Let's talk a bit about the purpose of including this ECDSA signature as part of the Ethereum transaction. There are really three purposes. The first one is authorization. Inclusion of the signature proves that the owner of the private key who created the signature, and who by implication is the owner of the sending Ethereum account, has authorized this transaction to spend the Ether or to execute the contract that it is targeting. The second purpose is that of non-repudiation, which means that once a signature has been included, it cannot be later denied that authorization was granted for that transaction to execute. The third purpose is integrity. This is one of the fundamental security properties, and in this case, it proves that the transaction data has not been modified or cannot be modified by anyone after the transaction has been signed. So these are the three purposes for including the ECDSA signature as part of the Ethereum transaction. We mentioned that a transaction can result in contract creation. Now, how does that happen? The creation transaction is a special transaction because it's sent to a special destination address called the zero address, which is really an address that has zero in all its bits. Now, this zero address is treated specially within Ethereum, within the smart contracts, and it becomes critical to some of the smart contract security properties that we'll talk about later on. But in this case, a contract creation transaction is sent to this zero address. It contains a data payload which represents the bytecode of the contract that is being created. And it may also contain an optional Ether amount in the value field, in which case the new contract that is being created will have a starting balance equal to this Ether value. Let's talk a bit about the distinction between transactions and messages. We've sort of used them interchangeably so far, but in the context of the protocol, they're actually very different. A transaction originates off-chain and it targets an entity on the blockchain. So it's coming from off-chain, targeting on-chain. Whereas a message, the origination and the destination are both on-chain. A transaction is produced by an EOA account where an external actor, external to the blockchain, sends a signed data package onto the blockchain. Now this transaction can trigger a message that does two things. It can trigger a message to another EOA, in which case it leads to a transfer of value, transfer of Ether, or it can trigger a message to a contract account, in which case it leads to the recipient contract account running its contract code and doing whatever that code is intended to do. Message, on the other hand, can be triggered in two ways. It can be triggered externally by a transaction, and the destination of that message could be another EOA or another contract account. Or a message could be triggered internally within the EVM. And this happens when a smart contract executes the call family of opcodes. And that leads to the recipient contract account running its code or value transfer to the recipient EOA. So this is a distinction between transactions and messages, something to be aware of. Now let's up-level a bit and try to understand how transactions fit in the context of a blockchain conceptually. Transactions are grouped together. They're grouped together and included within a block. Blocks are linked together in some fashion, and these blocks linked together form the blockchain. This is conceptually at a very high level how a blockchain is constructed. So blocks are batches of transactions. Every block therefore contains a set of transactions that are grouped together. But there's another critical aspect to this. Every block also contains a hash of the previous block. This is a cryptographic hash that is derived from the previous block's data. And this is really critical to how a blockchain works. This is really the fundamental reason why a blockchain is considered immutable, what lends itself to the blockchain's integrity. And the reason why that is so is because if someone were to change any component of a historical block, any of the transactions, any of the transaction data, the destination, or any other aspect, then that change would affect all the following blocks. All the hashes that are included in the following blocks would be different from the hash of the modified block. And this is something that anybody running the blockchain or looking at the blockchain would notice, and that would break the integrity of or the immutability of the blockchain. And to preserve the transaction history, blocks are ordered. So every new block created therefore contains a reference to its parent block. And similarly, transactions within the blocks are also strictly ordered. And all these critical aspects are really the reason why the integrity or immutability of a blockchain is maintained and prevent any fraud from happening. Now let's take a look at what an Ethereum node or a client is. An Ethereum node is really a software application that implements the Ethereum protocol specification. It communicates with other Ethereum nodes on the network in a peer-to-peer, P2P fashion. An Ethereum client is really a specific implementation of the Ethereum node. There are multiple Ethereum clients. There is Get, Open Ethereum, Erigon, Nethermind. Some of them are more commonly used and deployed than the other. Ethereum transactions are sent to the Ethereum nodes, and these nodes in turn broadcast them across the peer-to-peer network. This is really how Ethereum transactions propagate across the Ethereum network, reach the various nodes, get combined into blocks and result in the blockchain. Let's talk a bit about Ethereum miners. Ethereum miners are entities running Ethereum nodes on the network. They're the ones that receive all the transactions that we talked about. They validate them, they execute them, they combine them into blocks, and they also provide a mathematical proof known as proof of work, POW, which we talked about earlier. And for all this work, if the miner's block gets chosen to be part of the blockchain, then they are rewarded with what is known as a block reward. This block reward is currently 2 Ether, and it has changed over time, it has decreased over time. But this is really the crypto-economic incentive for miners to participate and to be honest on the Ethereum network. For all that work that they've done, they're rewarded with the block reward. Along with this, they're also rewarded with what is known as transaction fees. This is the Ether spent on gas by all the transactions included in that block. So block reward and transaction fees are really the crypto-economic incentives that are paid out to the miner whose block gets accepted into the blockchain. Block gas limit. Note that this is different from the gas limit which we talked about earlier that was specific to the transaction, the Ethereum transaction. This gas limit refers to the gas limit of the block. It is the total gas that is spent by all the transactions in that block. And this effectively caps the number of transactions that can be included within that block. So the block size is in fact not fixed in terms of the number of transactions, but it's really fixed in terms of the gas used by all the transactions. And the reason for that is every transaction can consume a different amount of gas. And this block gas limit is set by the Ethereum miners in a very interesting way by voting on the blockchain. So look it up if you're interested. And this is currently set to 15 million. And this is also something that has changed over time, that changes depending on the miners voting, and it also represents the level of demand there is for the block space on Ethereum. So transactions are sent, miners validate them, they combine them into blocks, and these blocks are propagated over the peer-to-peer network, and multiple miners are doing this process simultaneously, right? This whole act of receiving the transactions, validating them, producing valid blocks, doing the proof of work, creating these and propagating the blocks. This leads to multiple valid blocks at any level of the blockchain. But the canonical blockchain really needs to choose one valid block at any level. And this choice of that valid block is dictated by the ghost protocol, or the greedy, heaviest observed subtree protocol. This is really what makes or constructs a canonical blockchain, and this protocol also allows stale blocks up to 7 levels in this calculation, and the stale blocks are in Ethereum's nomenclature referred to as uncles or omers. More details of the ghost protocol are out of scope for this particular presentation. If you're interested, I would encourage you to dive into one of the references provided. This brings us to the critical concept of consensus. Decentralized consensus is really critical to any blockchain, and in the context of Ethereum, it refers to the Nakamoto consensus protocol that is adapted from Bitcoin. This really addresses the problem of which miner's block should be included next to create the canonical blockchain. And there are two components to this. There is the proof of work, and then there is the longest chain rule. There are many details that we won't be able to go through as part of this presentation. There's also a lot of research in this area of decentralized consensus algorithms. So for those interested, I would encourage you to dive into one of the provided references. Ethereum State is a mapping from the address of the Ethereum account to the state contained within it. As a data structure, this is implemented as a modified Merkle-Patricia tree. It's a combination of a Merkle tree and a Patricia tree with some changes that are specific to Ethereum. A Merkle tree is a type of binary tree that's composed of a set of nodes where the leaf nodes at the bottom of the tree, they contain the underlying data. And all the intermediate nodes between the leaf nodes and the root, they contain the combined hash of their two child nodes. So now if you visualize this tree, you have the data at the bottom in the leaf nodes and all the intermediate nodes combining their hashes, leading to the root node that is formed from the hash of its two child nodes. This is the top of the tree and is usually referred to as the root hash. A Patricia tree is a different data structure that's also called a prefix tree, a radix tree, or a trie, where the key value pair that it represents, or the key value pairs that are contained within it, have the values at the leaf nodes, and the keys let you traverse a path from the root of the tree to the leaves, so that the nodes that share the same prefix in the key also share the same path down the tree from the root to the leaves. Ethereum uses a combination of a Merkle-Patricia tree, and it's also modified to specifically suit the Ethereum data structures. In this particular case, it uses a hexary Merkle-Patricia tree, which means that each node has 16 children. And there's also a recent proposal to convert this to a binary trie, but that's out of scope. If you're interested in taking a deeper look at the data structures, then I would encourage you to take a look at one of the references for more details. We have referenced Ethereum proof of work multiple times until now in this module. This is what provides Sybil resistance and is fundamental to how the Ethereum consensus protocol works. But how does it look mathematically? This is technically referred to as ETH hash, and it's formally defined as shown in the equations here. We won't read out these equations or go into the depth of what they mean, and if you're interested in the underlying details, I would encourage you to look at the Ethereum yellow paper that explains all of this in fantastic detail. But at a high level, what a miner has to do is to determine a combination of mix hash m and nonce n for every block to satisfy the constraint on the difficulty for that particular block. This is a trial and error process, so the miner has to keep repeating the computation until a combination of m and n is found that satisfies the difficulty. And when this is done, it means that a sufficient amount of work has been done by the miner for this particular block, or in other words, this indicates that there is proof of work by the miner for this block. So far, we have said that the blocks in the Ethereum blockchain contain transactions, but there's more to it. Every block contains a block header along with the transactions and the headers of the armored blocks. Each block header itself has several components to it that are really critical to how the Ethereum blockchain functions. They contain several things such as the parent hash, the owner's hash, beneficiary address, and all the other components that are listed here. The parent hash, recall that it's the hash of the parent block's header, and this is what really chains the blocks in the Ethereum blockchain together to make it immutable and provides the fantastic integrity property of the blockchain. The beneficiary address is the address of the Ethereum account to which the block reward for mining this block and all the transaction fees collected from the mining of the transactions included in this block are transferred to. This is the address that is typically controlled by the miner who has mined this block. The block header also has the root hashes of the modified Merkle-Patricia tree, if you recall. There are three of them. There is the state root, transactions root, and the receipts root. There's also the concept of logs, which we haven't talked about, but we'll touch upon it in some of the forthcoming slides. There's a Bloom filter specifically associated with these logs that is part of the block header. Then there is the difficulty that we talked about in the context of the proof of work. That's also here in the block header. Then there are multiple components, multiple fields that are specific to this block. There's a block number, that's a value equal to the number of blocks that have been mined so far. Right? So this is sort of the number that indicates which block this is in the blockchain. Then there is the gas limit that's specific to this block. We talked about this, the block gas limit that really determines the number of transactions that can be included in this block. There's a gas used field that indicates the total gas used by all the transactions in this block. Then there is a timestamp that's derived from the Unix time that indicates at what point in time was this block mined. Then there are the two components of mix hash and nonce that are critical to the proof of work that we just talked about. So all these components form the block header. So the block header, as we just saw, contains three roots. It has the state root, it has a transactions root, and a receipts root. These are the root hashes of the modified Merkle-Patricia trees. So they are 256-bit in length, and they're constructed as we just explained. Now let's take an example of the state root and see how this is derived. This is really critical to how the Ethereum state is captured within the blockchain. The leaves of state root are key value pairs of all the Ethereum address account pairs. So the keys are the Ethereum addresses of the accounts, and the values represent the Ethereum state within that account. And recall that every Ethereum account has 4 fields: a nonce, a balance, a code hash, and a storage root. And if that account happens to be an EOA, an externally owned account, then the code hash and storage root don't really matter, so they don't contain anything in it. But if that account happens to be a contract account, then the code hash has the Ketchat 256 hash of the code that is contained within that contract account. And the storage root of that contract account has the root hash of another Merkle-Patricia tree, where the leaves represent the storage that is associated with that contract. So as we just saw, the block header contains 3 roots. It has the state root, which we just looked at. It also contains the transactions root and the receipts root. Transactions root should be fairly obvious. It's again another modified Merkle-Patricia tree where the leaves represent the transactions and you construct the tree, and the root hash is referred to as the transactions root. But what is the receipts root? What is a transaction receipt? A transaction receipt can be thought of as the side effects of a particular transaction that are captured on the blockchain. Besides any changes to the account state that transactions might make, there are other side effects that are captured on the blockchain for this particular transaction. It really is a tuple that contains 4 items. It contains the cumulative gas used, set of logs, and then the Bloom filter specifically associated with these logs, and it also contains a status code. The gas used represents the total gas used in the block until now, until right after this particular transaction has happened. So in some sense, it captures the ordering of the transactions within the block. The logs are related to the concept of events in Solidity, which we will study in the Solidity modules. These are events that can be generated by any transaction that are captured on the blockchain, and they're really critical to how off-chain components, user interfaces, and other components monitor what's happening with a smart contract. Now, there's also a concept of indexed parameters for every event, so that one can query particular parameters of that event in a faster manner. These are captured, or these are enabled by the Bloom filter that is associated with those particular logs. And then there is a status code that indicates what really happened with that transaction. We have talked about gas in multiple contexts in this module, but let's review this in the context of a particular transaction. The ether that is used to purchase gas for a particular transaction is credited to the beneficiary address that we just saw was specified in the block header. This is the address that is typically under the control of a miner, and all the transaction fees from this transaction and all the transactions in the block mined by that miner is credited to the miner's beneficiary address. Then there's also a concept of a gas refund. So if you recall, every transaction has a gas limit that represents the maximum number of gas units that the transaction is paying for. But then there is also the actual amount of gas used by this transaction. So the difference between the gas limit and the gas used is refunded back to the sender of the transaction, and this is done at the same gas price as indicated in that transaction. All right. So to summarize what we have reviewed so far, we have taken a look at the motivation behind the Ethereum blockchain, some of the higher level concepts, the properties of the blockchain, the purpose of the blockchain, and then some of the underlying primitives related to cryptography, the concept of transactions, concept of accounts, states, the concept of gas, Turing completeness, how all these things work with each other. We have taken a look at what is a blockchain from a data structure perspective, the components of blocks. We've also taken a look at what the consensus algorithm is and why that is critical. we have taken a look at the proof of work. So a lot of these concepts, and we have taken a high-level look, and the details, of course, are there are a lot of details. So I would really encourage you to take a look, deeper look at the references provided, the white paper, yellow paper, and there are so many other fantastic references that are provided as part of these modules. So take a look at them to sort of get a really firm understanding of these fundamental concepts. But now it's time to switch gears and take a look at the execution component of the Ethereum blockchain. And this is referred to as the EVM, the Ethereum virtual machine. This is really the runtime environment where all the smart contracts that are really fundamental to Ethereum, what makes Ethereum the next generation blockchain, this is where they run. So we'll be taking a deeper look into EVM, the architecture of the EVM, the various opcodes that actually enable this execution and so on. But before that, let's recall that EVM is a quasi-Turing complete machine. It's Turing complete for the reasons we talked about, because the underlying programming language supports arbitrary logic, unbounded complexity. But it's also bounded, the computation is really bounded by the concept of gas, the amount of gas provided as part of every transaction. So this is something that is really fundamental to how the EVM functions and something to be kept in mind. So the Ethereum code runs within the Ethereum virtual machine, or EVM. And this code is written in a low-level, stack-based language referred to as the EVM code. And this code consists of a series of bytes, therefore referred to as a bytecode, where every byte represents a single operation. So the opcodes are very simple, and each of them is a single byte. Now let's take a look at what the EVM architecture looks like. EVM is a very simple stack-based architecture. And what this means is that the EVM instructions operate on the stack. The operands for those instructions are placed on the stack, and the output of those instructions is also returned on the stack. There's no concept of registers, virtual registers, or anything like that. The architecture is made up of four fundamental components: the stack, the volatile memory, the non-volatile storage, and call date. The volatile or non-volatile refers to the persistence of the data that is placed within the memory or storage. And we'll take a deeper look into each of these in the forthcoming slides. And every architecture has a concept of a word. In the case of the EVM, the word size is 256 bits. And it's believed that this was this word size was chosen to facilitate some of the fundamental operations around the Keccak 256 hash scheme and the elliptic curve computations. Now, how does the stack look like? EVM, like we just said, is a stack-based architecture. It has 1024 elements in the stack, and each of those elements is 256 bits in length, equal to the word size. And EVM instructions are allowed to operate with the top 16 stack elements. Most EVM instructions operate with the stack because it's a stack-based architecture. And there are also stack-specific operations such as push, pop, swap, duplicate, and so on. We'll take a look at these categories of instructions in the forthcoming slides.